Hello, welcome to the first video in this series about differential geometry. The first few videos we're going to be covering multilinear algebra. And so today the first topic we're going to cover is the dual space. So what is the dual space? Suppose you have a vector space. So let me remind you of what a vector space is. A vector space, it's closed under scalar multiplication. So a vector space, I'll call it V, and it always has associated with it a scalar field. So this field is either R, or the complex numbers, or Q, which is the rationals, or any other field you like. So a field is just anything you can divide, multiply, add, and subtract in. So a vector space is closed under scalar multiplication. This means that AX is in V whenever A is a scalar and X is a vector. Second of all, it needs to be closed under addition. And third of all, it needs to have all the properties that come with the field K. So, for example, commutativity of addition, and the distributive property, and so on. And finally, it needs to have these objects called identities. So the identity in a vector space is the 0 vector, and the idea is that 0 plus x is just x. And similarly, 0 times x is the 0 vector. So these define a vector space. They're called the vector space axioms, and I'm going to relate them to the dual space. So let V be a vector space, and let's consider some maps on V to R. So if you have a map alpha, which takes in vectors and spits out numbers, then this map is called a functional. Let me write K for generality. And if this map is linear, it's called a linear functional. So if alpha is linear, it is called a linear functional. And the neat thing about linear functionals is that they are typically in one-to-one correspondence with elements of the vector space. So let me show you an example of this. You can write a vector in column form. So let x be a vector, and I'll write it in column form, x1 dot 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 xn. Then there's an associated functional to x, which is x transpose, and it's a row matrix. And if you took x transpose of x, you're going to get the matrix multiplication of these things. And this just gives you x dot x, which is a scalar. So this is an example of a linear functional, and here you can see that there are definitely exactly as many functionals as there are vectors, because every functional can be written as basically the transpose of some vector, or the adjoint is the correct terminology for this operation. And we can usually find a isomorphism between the two vector spaces. So this vector space of linear functionals, you've all seen that you can write matrices as a vector space. So here you can obviously see that a linear functional forms a vector space. So the space of functionals is called the dual space. So I'm going to define that. Dual space. So V star is defined as the dual space, and it's the set of all alpha which are maps from V to the underlying field of V such that alpha is linear. So these are all linear functionals. On V. So this is the essential stuff about the dual space. Something to note is that theorem, if V star and V are finite dimensional, then V is isomorphic to V star. That means that there exists a linear invertible transformation from V to V star. So this basically puts V and V star in correspondence with one another. The example I like to use is the transpose, so let me do that in a new color. My pen's not working. Okay, so example. So Rn is the space of all column vectors of dimension n. And Rn star is therefore the space of all the transposed column vectors. And these row vectors are going to be called covectors. And these things are vectors. So vectors and covectors are related by a transpose. That's why we call them co. In fact, if you have an inner product, so let me define that real quick. I need to figure out how to turn this off. I'm going to lose my mind. Goodbye. So if you have an inner product, so an inner product is a product between two vectors that returns a scalar, and it's linear, positive, and non-degenerate. Non-degenerate meaning that x dot x is 0 if and only if x is the 0 vector. So if you have an inner product, then you can always find a correspondence between the dual space and the vector space. So for example, if you have a vector space V, then with an inner product, you can always take x and return alpha, where alpha subscript x, where alpha x of y is defined to be the dot product of x with y. So in the case of Rn, this map here, this correspondence, is always the transpose. But that is not always the case. For example, if you have Cn, then Cn's corresponding inner product is going to be x conjugate transpose times y, in which case now our correspondence becomes x maps to x conjugate transpose instead of just x transpose. So that's a good little example of when it changes. Another example would be in an infinite dimensional vector space. So for example, pick the polynomial space over R, which is just a set of all polynomials. With real coefficients. Then there's an inner product on P of R, which is given by x, y equals the integral of, actually I shouldn't use x here. I'll use f and g. So fg is the inner product of fg times some extra weight function dx. And so you can usually find a correspondence. F maps to the map alpha f, where alpha f of g is defined to be the integral of fg w dx. But this mapping right here, I'll call it L, this mapping is not necessarily invertible. In fact, there are definitely more linear functionals over the polynomials than there are polynomials themselves. And this is a topic of study you might come across in PDEs or ODEs too, or any course on functional analysis where you're doing infinite dimensional linear algebra. But for now, we're going to just deal with finite dimensional vector spaces. So now we know what the dual space is, and I'm going to take a quick break for you to think about it, and then we'll go on to tensor products. Alright, so many of you have heard of tensors before. However, they're usually like a scary thing that people like to tote around as being some advanced physics stuff. But really, tensors aren't that complicated. Really, what people mean when they are talking about the complicated tensor stuff is tensor fields. And we will go to those later in the course, but for now we're just going to talk about tensors. So let me ask you a question. What happens if I want a map M, which will take in perhaps n covectors, or sorry, n vectors, and m covectors, so alpha 1 through alpha m. So m is a map from v to the n with the Cartesian product of v to the m star. Let me fix this. And it will return a real number. So, or of course a general element of the field underlying the vector space. So we want this map to be linear in all of its arguments. So m of dot 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 axi plus b y needs to split. And this applies to the covector argument as well. So such a map is called multilinear. So for all I in 1 dot 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 n or 1 dot dot m. Such a map is called multilinear, and well, really it's a multilinear functional. And it's defined on Vn times V star m. And these objects are what we really mean by tensors. So this phrase right here is the same as n comma m tensor over V. So the space of all such multilinear functionals is called tensor product space, and it's written as this. So V tensor dot 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 tensor V, and then we're going to tensor it again with V star m times. So this is n times, and this is m times. And what this tensor notation means is that we're going to take in, actually, sorry, these should be starred, and these should not be. I left something out, right? Because the input is a vector. So when you input a vector and you get a number, you want an element of the dual space to be acting on the vector. So really, this is like the combination of n covectors and m vectors. So we're going to apply these things to the, or we're going to plug these things into the covectors, and we're going to plug these things onto the vectors that you input. So let me show you an example. Suppose alpha 1 is some covector. I'll pick 2, 3, I don't know. And alpha 2 is another covector, 1, 5. Then you can tensor alpha 1 and alpha 2 together. And if you were to apply this to two vectors, you would end up with alpha 1 of x times alpha 2 of y. That's really all there is to it. This is the entire idea behind the tensor product. If you take smaller covectors of order 1 and you tensor them together, you just apply the first one in the tensor product to the first input and the second one in the tensor product to the second input. So you could do alpha 1 tensor alpha 2 of, let's say 1, 2, 3, 4, and you'll get 2, 3, 1, 2 times 1, 5, 3, 4. And this is just 2 times 1 is 2, plus 3 times 2 is 6, so that's 8 times 3 times 1 is 3, plus 4 times 5 is 20, so that's 23. And this is a big number that I can't do in my head right now. Great, so now you've seen the basics of the tensor product. So in general, let's try to find a basis for tensor product space. So let's define it. Tensors of rank n comma n. We're going to name this v star to the n with a little tensor product here. And then we're going to tensor this with v to the tensor m. And this notation just means take the tensor product n times. And it's really all multilinear functionals with n vector inputs and m covector inputs. Great. So, of course, this is over V. And if we were to find a basis for this, so a basis, remember, is a set of basis vectors. So let E1 through En, actually I'm going to do uppercase notation for this. E1 through En, it's a basis for, oh no, sorry, I do need lower indices. So this is a basis for V star tensor n, or sorry, V star. Right. Okay, I screwed up here. So there are k basis vectors because I'm going to let the dimension of V to be k. There we go. Now let E1 dot 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 ek be a basis for V. So here the idea is that the basis vectors have the property that ei in the lower is a covector, and when you apply it to ej in the upper, you get 1 if I equals j, and 0 if I does not equal j. So this notation here is going to be called the Kronecker delta, and we write it as a delta with an I in the lowercase and the j in the upper index. So this is an orthonormal basis. Because they're orthogonal and they're normalized. So then a basis for V tensor n is going to be the set of all possible combinations of these EIs for any amount less than k. So we're going to make n less than or equal to k, and it's going to be E of I1, comma, tensor, sorry, E of I2, tensor, dot, 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 up to E of In, where I1 through dot, 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 In are integers from 1 to k. So if you were to write out, for example, 2, 1 is going to be, oh, sorry, tensor something else, like 1, 2. This is going to be E2, E1, plus E2 tensored with E1 plus 2 E2, and this is equal to, now the tensor product is distributive. It has the same properties as multiplication. So you can do 2 E1 tensor E1 plus E2 tensor E1. Oh man, I'm so sorry, I fricked up. These should be lower indices because these are covectors. Okay, there we go. So now it's 2e2 tensor e2. And finally, I'm missing one that's 4e1 tensor e2. 2, 1 here. Okay, so this is essentially the tensor in a basis notation. And you'll notice that there are only really, there's 4 unique possibilities when you combine these two things. So we can see that the dimension of V tensor, sorry, that's tensor product, V tensor n is equal to 0 if n is greater than k. Strictly greater than. It's going to be otherwise k choose n if k is less than or equal to n. And of course there are no such thing as negative tensor products, so this is a final result. And of course if you took V tensor n and you combined it to get a tensor with covector indices, you could get V star tensor m, and the dimension of this would just be 0 if n is greater than 2k, because here we're combining them, right? Now this should be k, and m is greater than k, and it should be k choose n plus k choose m, I believe. I think this makes sense. It might be the product of the two. That wouldn't make as much sense, so I'm going to leave it like this. You can feel free to look this up and confirm for yourself, so I'm going to leave a question mark here. Okay, so exercise. I'm going to not do this. Find dim of tensors of rank nm over V. Great. So now we've covered tensors, and you might be a little bit confused because these objects are a little bit simpler than you might have thought. They're all just multilinear functionals, and they have n vector inputs and m covector inputs. Now I'm going to talk about something called covariance, and I'm going to give you a second to just rest before I do that. Okay, I've actually decided not to cover contravariance. Instead, I'm just going to do a short thing on Einstein notation. So let, for example, an object V be equal to the sum of VI's times some basis vector EI's. Then wherever the index I appears both in the upper location and the lower location, we ignore the sum symbol. So this means that we're going to write V as just VIEI, and we're going to assume that the sum is there, so implicit. Another example would be if T is a tensor, then T can be written as a sum of components, and it's got n vector components and j or m covector components. So this thing, sum is assumed. So we've gotten rid of the sum over I1, the sum over IN, or I2, and so on. So we really didn't want to write out all these sum symbols. Get rid of sigmas. So this basically just shortens our expressions. We don't have to write all these big sum symbols every time. We can just see that there's j's up here and j's down here and just sum over them. So this makes life easier, and we'll see this next time. In the meantime, thanks for watching, and next time we'll cover probably more tensor stuff. I'll have to think about it. Bye bye.